What I said before when I introduced the distribution of the square of a standard normal as a chi-squared with 1 degree of freedom, well, I think I was implying that we could have a chi-squared with more than 1 degree of freedom. And we can, and in fact that's the distribution of the sum of n independent standard normals, each squared, then added together. So if I've got x1, which is a standard normal, x2, which is a standard normal, xn, which is a standard normal, these are all independent of each other. I square each one, I add up all n squares, then what I'm claiming is that that defines a chi-squared with n degrees of freedom. Now, deriving the density function for that directly, if you really want to do an n by n Jacobian matrix for a change of variables, by all means do that in your spare time. I think that's one more for the calculus junkies, not something I'm inclined to do. So what I'm going to do here is I'm instead going to say this is the density function, and then we're going to justify that that is the case. How are we going to justify that that's the case? Well, we're going to do it by induction. But before I can do that, I need to note that, in fact, this normalizing constant in the denominator, gamma of n over 2, I need to note that gamma of a half is the square root of pi. You will have to take that one on trust, or you can check the definition of the gamma function to prove that. But we'll take that as read before we start the inductive proof. Now, to start the inductive proof, we just simply have to justify that this chi-squared with n degrees of freedom density function that I'm claiming matches with what we thought for a chi-squared with 1 degree of freedom. And if I set n equals 1 in there, hopefully you'll see that 1 on the square root of 2 to the n is just 1 on the square root of 2. If you believe me that gamma of 1 over 2 is the square root of pi, then the rest of it collapses back to just e to the minus s on 2 times s to the minus a half, which is exactly what I got for the chi-squared 1 density. So given that I'm convinced that my formula for the chi-squared n agrees with my formula for the chi-squared 1 when n equals 1, all I have to do now is I was claiming that if I added n squared normals, then I would get a chi-squared n. Now I know that's true for adding 1 to something, so all I have to do now is show that if I have this formula for chi-squared n, and I've got a chi-squared m, that if I add those together, then I'll have a chi-squared with degrees of freedom m plus n. Because of course the distribution of m squared normals plus the distribution of n squared normals should be the distribution of m plus n squared normals. Now I know that that's true for 1, so if I add 1 and 1, I should get chi-squared 2. Then if I add 1 and 2, I should get 3, and by induction, that should be true forevermore, if I can show that the distribution of a chi-squared n plus a chi-squared m will be the same as what I'm claiming is the distribution of a chi-squared m plus n. So the way that we do that is we introduce the density functions of the chi-squared n, which I'm calling the distribution of s, and the chi-squared m, which I'm calling the distribution of t. These things are independent, so their joint density is just the two functions multiplied. Now if I do the change of variables, the one I'm really interested in is u, which is the distribution of s plus t. That's what I need to match up to the distribution of the chi-squared with m plus n degrees of freedom. But I'm also going to set this other change of variable, which is s over s plus t. When I invert those change of variables, u equals s plus t and v equals s over s plus t, I get s equals uv and t equals u1 minus v. So when I do the Jacobian associated with this change of variables, I get that the absolute value of the determinant is u. What we now need to do is take this joint density of the original distributions, s and t, and put in the change of variable s equals uv, t equals u into 1 minus v, and then multiplied by the absolute value of the Jacobian's determinant, which is u. So I'll put those in. Hopefully you can see. Maybe pause it at this point if you wish. But replacing the s with uv, replacing the t with u1 minus v, and so on, I will get that statement. Now there's a lot of tidying up to be done in there, but hopefully you'll sort of convince yourself that that's correct. Now I've tried to pull some of the terms together. I've pulled, for example, there's an e to the minus s on 2 multiplied by an e to the minus t on u in the original, which is of course e to the minus s plus t on 2, which is a e to the minus u on 2. So I've already done a little bit of tidying up. I've also considered the ranges of the variables, because if s and t can be anything between 0 and infinity, then s plus t can be anything between 0 and infinity. So that's u. Whereas v is constrained to be between 0 and 1, because it was s over s plus t. So because t is non-negative, s plus t can't be less than s. So I have a fraction where the numerator has to be no bigger than the denominator, so it has to be no bigger than 1. We can then simplify it to this. Pause this if you like and flick back to the previous section, previous slide. When I say simplify, I've partially simplified. I've pulled all of the u terms to the left, all of the v terms to the right. But what I have also had to do is I've introduced this gamma function evaluated at m plus n over 2, top and bottom of this fraction. So I haven't changed it, I've multiplied it by it and divided by it. Why have I done that? Well, the main reason is that we can recognize now that the front of those terms, which depends on u but not v, is the density function of a chi-squared with m plus n degrees of freedom. And this is all I needed to complete the inductive proof. I needed to show that if I had a chi-squared m, i.e. the sum of m independent squared standard normals, and I added a chi-squared n, the sum of n squared independent standard normals, then I'd get the sum of m plus n independent squared standard normals, i.e. a chi-squared with m plus n degrees of freedom. And because we established this for the base case of m equals 1, we have this inductive proof that what I claimed was the density function for a chi-squared with m degrees of freedom is. Now mathematically we've also got a buy one get one free here. I've also justified that the distribution of s over s plus t, where s was a chi-squared with m degrees of freedom and t a chi-squared with n, is a beta distribution. So is strictly only on the range 0 to 1. And we saw this same result, or a similar result before, when we derived the ratio of gamma variables in the previous week's materials. I'm less interested in the beta result right now, but I've established the chi-squared density. So I can now move forward with confidence that this is the density function of a chi-squared. But what does this look like? Well, as I increase the degrees of freedom, I get potentially very different shapes. The mode could be at 0, or it could be an interior mode. And the larger the degrees of freedom, the larger the expectation of this, and the greater the mode is as well. Now, if n is 1 or 2, we'll get a mode at 0. If I've got more than 2 degrees of freedom, the mode, so the peak of the distribution, will be at n minus 2. Now, it's not particularly difficult to prove what the expectation of it is, because it's the sum. Chi-squared n is the sum of n independent standard normals. A standard normal has variance 1 and mean 0, so it has expected square 0. So I'm adding n things with expectation 1, so I'm going to get n. So a chi-squared with n degrees of freedom has expectation n.